Last time we started talking about the minimum cost path problem, and we had a chance to formalize that problem, and also then to consider two unusual cases that could arise. So one unusual case would be, suppose I go looking for a minimum cost path from vertex u to vertex v, but I'm unsuccessful in finding one because there is no path of any kind from vertex u to vertex v. In the context of a cost interpretation, we could argue this corresponds to a case where the cost of travel from vertex u to vertex v is infinity, which is to say, no matter how much money you have, there is no amount of money that could buy you a ticket from vertex u to vertex v. We called this the infeasible case, where there is no path whatsoever. There are no solutions available, so we can't choose the best solution. Now, this particular unusual case isn't that sensational because we've seen this already in various other contexts in this course. It's quite natural to us that there could be two vertices in a graph where one is not reachable from the other. Now, the other unusual case was a bit more strange, and it's called the unbounded case. And that's the case where there is some way of getting from vertex u to vertex v, but it's not really appropriate to talk about the minimum cost of travel because there's a way of making the cost of getting from vertex u to vertex v arbitrarily low. And this is the unbounded case where we could argue that the cost of travel from vertex u to vertex v is negative infinity. That is, you could make the cost arbitrarily low. In other words, you could make as much of a profit as you want if you wanted to travel from vertex u to vertex v. We were able to characterize the situation in which this case arises as being the situation in which there is a cycle. Somewhere in the graph, there exists a cycle of some length where the total cost of travel all the way around the cycle is negative. So an example of that would be, consider this cycle here, where the cost of travel along this edge is negative 1,000. That by itself is no problem. Negative weight edges can exist and should be allowed to exist in our cost interpretation. The problem is, if I start here and I travel all the way back around again, even though I'm at the same place where I started, I have now made a profit. And in the grand scheme of things, I sort of made a profit by standing still. I mean, that is, I did go around the cycle, but I ended up exactly back where I started. If such a situation exists in a graph, then there could be these cases where travel from one vertex to another has an apparent minimum cost of negative infinity, which of course makes no sense because infinity is not a number, and so we treat this as sort of a converse special case to the infeasible case. It's a case where it's maybe a little bit too feasible to travel from vertex u to vertex v. And for the time being, we have argued that if a negative cost cycle exists in a graph, maybe the whole graph is a write-off. Sure, there could be solutions to the minimum cost path problem for isolated vertices within that graph, but nobody's going to blame you if they hand you a graph that has a negative cost cycle and you can't solve the problem. So our two special cases were infeasibility, the case where travel from u to v costs an infinite number of dollars because you can't do it, or unboundedness, where the cost of travel, the minimum cost of travel from vertex u to vertex v is negative infinity because you can earn an arbitrary profit from getting to, for the case of traveling from vertex u to vertex v. Okay, and then during the last lecture, the other main objective we had was to derive and prove the correctness of an algorithm to compute minimum cost paths. And we did that producing something that is called the Bellman-Ford algorithm. And the formulation that we ended up with at the end of the last lecture was pretty convenient for showing the running time. So we were able to figure out that this outer loop, we could restrict it to always run for size of v iterations. Even though there is a formulation where the loop might end earlier, the proof of correctness that we wrote allowed us to rewrite the algorithm in this form, showing that the running time of the Bellman-Ford algorithm, in other words, find me minimum cost paths from some particular starting vertex v start to all of the other vertices in the graph that are reachable from v start, the Bellman-Ford algorithm required this amount of time for that task. So size of v times size of e. And the question we left off with last time was, can we do better than this? Okay, I want to lay out a few reasons why I think the answer might be yes, or it's at least worth looking into. And I mean, spoiler, we have a whole lecture we're going to do on this, so apparently the answer actually will be yes, for lots of meta reasons. Okay, so meta reasons that we can be suspicious that we might be able to improve on this include the fact that up until this point in the course, we have had pretty good luck with making graph algorithms fast. So up until the point where we first saw the minimum weight spanning tree problem, we were in fact able to solve all of the graph theoretic problems we wanted to solve in linear time in terms of the number of vertices and edges. That was pretty good, even though we occasionally encountered much slower algorithms on the way to our linear time solutions. And then when we encountered the minimum weight spanning tree problem, And I'll just pause here and observe that the minimum weight spanning tree problem does seem to have a few similarities to the minimum cost path problem. In both cases, we're developing a sort of tree involving an edge-weighted graph, and we're trying to minimize some statistic derived from the weights of the edges. And so maybe there is some similarity between those two problems, something to think about. But we noticed when we were studying the minimum weight spanning tree problem that we would encounter some algorithms. Our initial attempts had this running time. But we were able to bring that running time down to a much more efficient algorithm. We actually had several ways of doing that. Jarnik's algorithm, Kruskal's algorithm, and Beruvka's algorithm all had faster running times than this. Okay, so there's some overarching sort of meta reason why it might be useful to look into faster algorithms for this case. I mean, there will be, some occasion where maybe the best we could ever do is this, but maybe that's not this application here. So that's worth a try. Now, a much more local and practical reason that we ought to look into faster algorithms is that our focus in the previous lecture, where we were deriving this approach, was to come up with some algorithm to solve the problem that we could prove the correctness of. That was our priority, because of course it's better to have a working solution than a fast broken one. And in the service of that goal, while we were deriving this algorithm, we made a few choices that we could admit at the time seemed a little bit wasteful. So in the process of deriving this, before we had proved correctness, there were a few places where we made a choice that would keep the algorithm simple, and therefore hopefully easier to prove the correctness of, while also apparently maybe taking a bit of extra time, maybe wasting some time. And now that we know this algorithm is correct, maybe that's one avenue we could follow to try and speed it up. Now, the algorithm we are going to eventually come up with is a bit of a tangent off of this one, but I want to begin by talking about obvious reasons why this algorithm might be a little bit too slow, and maybe ways we could exploit that, make observations about how the algorithm behaves to speed it up. So in particular, this inner loop here, so remember that the Bellman-Ford algorithm, for some number of iterations of the outer loop, and we determined that in the proof of correctness last time, that size of v iterations is sufficient, but maybe fewer could be sufficient in some cases. We run this outer loop for that number of iterations, and each iteration we relax all of the edges of the graph. That is the sort of core mechanic of the Bellman-Ford algorithm. But the thing here is that the inner loop relaxes all of the edges of the graph at each iteration of the outer loop, searching for any edges that incrementally improve my solution. The issue is we observed during the examples we did last time that there are lots of edge relaxations that clearly won't help us, and that we might actually know that in advance. So at every step, even edges that couldn't improve my current tree get considered, such as edges that are already in the tree. So obviously if an edge is already in the tree, why bother relaxing it again? Nothing's going to change. Or edges where the total cost is actually, the cost of the source vertex to travel to the source vertex is currently infinity. So for example, if I have this vertex u here, and the cost of travel to u is currently infinity, well then what's the point of even looking at this edge? Because the destination vertex v, for example, well, if its cost is currently infinity, well, then adding this edge isn't going to improve anything. And in the strange event where the cost of travel to v is currently a finite number, well, clearly no path that takes me through a vertex that costs infinity to reach is going to help me improve my solution in terms of cost of travel to v. And yet, the Bellman-Ford algorithm at every single iteration tries to relax every single edge, even edges that clearly couldn't help anything. Now, arguably, this is because the algorithm is simple enough that there's no way to identify the bad edges in advance. I mean, if I want to skip over edges like this one, then actually this test does ignore that edge. If I reach the edge and I perform this test here, it will come back false and I won't relax the edge. I guess what I'm bringing up is, by iterating over every single edge, I have to wade through a bunch of edges individually that each fail this condition, even though if I were more careful with the edges that I consider, I could avoid all of them in general. So cases where I have a vertex whose cost of travel is currently infinity are cases where a vertex is so far away from the current tree that there's no way that it could be used to improve my solution at this time. Maybe if I kept better track of the state of my current tree and which vertices could help me and which vertices might not, I might be able to completely avoid considering certain edges. We also saw last time, incidentally, so it just came up in passing, that this loop here just says iterate over all the edges of the graph. It doesn't give any indication of how I'm supposed to do that. And so naturally, if I were to go to implement the Bellman-Ford algorithm, or if you were to do it, probably the order of edges that you would use is whichever one is convenient for the underlying data structures that you're using. So for example, if you're representing your graph using an adjacency list where you have each vertex mapped to a list of its neighbors, and so something like this, A, D, G or something, then probably the way that you would loop through all edges is you would loop through the adjacency list, loop through all the vertices in the list, and then for each vertex, loop through all of its neighbors and consider the corresponding edge. Fair enough. And that would work just fine. But this algorithm doesn't prescribe any particular order. And because during my examples last time, I wanted to be consistent, so I wanted to use the same ordering every time so that if you practice the algorithm, you get the same result I do in the same order, I tried doing a variety of different orderings, like alphabetical ordering and reverse alphabetical ordering. And in trying that, we noticed that the algorithm can behave quite differently if I consider edges in alternate orders. And that was sort of a hint that maybe the ordering of the edges, if we know how to treat it properly, could speed up the operation of the algorithm. So let's start with that point. Let's start with considering the ordering of edges. So consider this graph here. And suppose that I decide to run the Bellman-Ford algorithm on this graph using this vertex over on the left as my starting vertex, and where I consider edges, if I want to loop through edges to relax them at each step, I consider them in alphabetical order. And so remember that alphabetical order in this context means I would consider the edge AB first, then the edge AC, then the edge AD, and those would all come before an edge like, for example, BE, and that would come before an edge like CF. I just consider the edges in alphabetical order. That's a completely synthetic and arbitrary order, but it's useful for me to use on these slides because it's an easy order for you to replicate if you want to try the same example. Suppose we try that. If I do one complete round of edge relaxations, one iteration of the outer loop, as it happens, I get this tree, which actually is optimal. This is the minimum cost path tree, after only one round of edge relaxations, on a graph with 8 vertices, where normally I would have to do 8 iterations of the outer loop. But here I only need 1. And what we'll see in a minute is there is strong evidence that the reason why the algorithm is so fast on this particular case is just because of the ordering in which I considered the edges. So we can make the argument that with this particular graph and with this particular choice of edge ordering, the algorithm requires linear time. Now actually, stating this with asymptotic notation is bending the rules a bit. It's sort of weird to talk about the asymptotic complexity of a single input, because usually, of course, asymptotic complexity is based on how the input size scales. So sorry about that. Maybe I should just say V plus E time. In any event, with this particular lucky input, with this particular lucky case of this choice of start vertex on this graph, with these vertices where edges are considered in alphabetical order, I end up getting the minimum cost path tree really quickly after only one round of edge relaxations. Okay, let's consider the same graph again, only this time I have relabeled all of the vertices. That's the only change I've made. So if you flip back and forth, you will observe the set of edges is exactly the same. The edge weights are exactly the same. The number of vertices is the same. I have just decided to rename all of the vertices. In this case, what I've done is I've renamed them so that I guess if you go through the vertices in alphabetical order, you're sort of going from right to left this time instead of left to right. And yet, I still want to compute the minimum cost path tree rooted here at vertex H. So I'm still going to consider edges in alphabetical order. And I should actually observe before I do this that another way of doing the same example would be to then redo the previous example where this is still called vertex A, but consider edges in reverse alphabetical order. I've chosen to do it the other way around where I still do alphabetical order, but I relabel the vertices because I feel like visually it's more obvious what's going on in that case. Okay, so in this case, what that means is that because I'm going through edges still in alphabetical order on my relabeled graph, the first edge I would consider would actually be edge AC, which is this edge. And the second edge would be edge AD. And then later on, I might consider, I guess the next one I consider would be BA. And then if I keep going, after a while, I'll eventually consider edge DG, and then edge ED sometime after that, and way down at the bottom, way down near the end of my inner loop, I finally consider, for example, edge HG. So in this case, compared to the previous example, the edges that are immediately incident, or in general close to my starting vertex H, get considered relatively late in the process. Now we know that regardless of how I label my vertices, the Bellman-Ford algorithm will succeed. We will actually find the minimum cost path tree because, we proved the correctness of the algorithm last time. Let's see how long it takes. So after one full round of edge relaxations, the only things in my tree are these vertices here. Now, I haven't necessarily found minimum cost paths to any of them yet, because for all we know, the minimum cost path, for example, to vertex G may not involve this edge. We already know that's the way the algorithm works. And so as it turns out, the minimum cost path to vertex G actually runs sort of like this. But notice that after one complete instance of the inner loop, after relaxing all edges once, my tree is pretty small compared to what I had earlier, where I was able to do one iteration and get the full tree after one iteration. After 2 rounds of edge relaxations, I have this. Okay, so my tree still doesn't contain everything. After 3 rounds, I have this, but this isn't the optimal tree. I actually have to go all the way to 4 rounds to reach the optimal tree. And this is the same graph as before. All I've changed is the labeling of vertices. And yet it took the algorithm quite a bit longer to converge to the final minimum cost path tree. And I would argue that this example on its own, these 2 different labelings, is evidence that the algorithm seems to be quite sensitive to the order in which I consider edges. And it's worth looking into. Because what I want to figure out is, we know already that, sometimes you have a worst case input and sometimes you have a best case input. But I guess my argument here is that this graph is the same graph as my earlier case. How is it that relabeling vertices can take me from a really lucky case, where everything happens in 1 iteration, to a pretty unlucky case where I need 4 iterations? I'll also observe that actually 4 iterations isn't the most unlucky, because I have 8 vertices here. I might require 7 iterations for all I know in some cases. But still, 4 iterations is a lot more than 1. So what I want to ask is, why is the algorithm so sensitive to the order in which edges are considered? And for the sake of the example, basically what I'm going to do is I want to focus in on the path, the minimum cost path from vertex H to vertex G in this labeling of the graph. And I want to see how we find that path. Okay, so when I do my first round of edge relaxations, I have this tree here, which only includes these vertices in the tree. Everything else is inaccessible at this point. Now, the true minimum cost path from vertex H to vertex G is HEDG, as I outlined a minute ago. Basically, the question I want to investigate is, why does it take so long to latch in these 2 edges into my minimum cost path, to choose this in preference to my current choice, which is the edge HG? And what we can observe is basically, I'm going to need to relax these 2 edges before I can get them into my tree. I have to relax those edges, and I consider that if I do one more iteration of my outer loop and I relax the edge ED, well, of course, at that point, vertex D will be brought into my tree, because there will be a path of finite length that takes me to vertex D. But then I think about the edge DG, and I realize that in the next iteration of the inner loop, the edge DG will be relaxed before the edge ED, because I'm going in alphabetical order. And of course, it makes no difference what order I chose to go in. No matter what ordering I chose, a similar situation could happen for some graphs. So the edge DG will be considered first, and then later the edge ED will be considered. And I know in any event that at the next iteration, when the edge ED is finally considered, it will be brought into the tree, because it'll give me a path to vertex D. What I'm wondering is, because I consider edge DG first, there's no way that I'm going to complete that path on the second round of relaxations. So during the next round of relaxations, edge DG is relaxed before edge ED, and the state of the algorithm at that point is what we see here. So at this point, when I look at the edge DG, the cost of travel to vertex D is still infinite, which of course means that this edge can't help us, so the relaxation fails. Nothing interesting happens, the tree doesn't change. Okay, so edge DG is not added to the tree. Later on in that iteration, I do find edge ED and I relax it. Okay, so at the end of 2 rounds of relaxations, vertex D is in the tree, because by then I have seen the edge ED. And so we sort of know that after one more round of relaxations, when I look at the edge DG again, well, now vertex D has a finite cost, and so I will be able to bring that edge into the tree. And so basically an observation we can make here, I think I've been saying this implicitly, is that because this path, which we know is actually, we happen to know this external to the algorithm, so we already figured this out earlier, we know that the path HED is a minimum cost path from vertex H to vertex D. And now that that path is in the tree, we know that the tree is never going, or that that path will never be removed from the tree. That is, this path will remain in the tree for the remainder of the algorithm, because there is no lower cost path to vertex D. And therefore, therefore, we're guaranteed when we finally see edge dg in the next iteration, because we know that edge dg is on the minimum cost path to vertex g, we are guaranteed to find the path hedg and add dg to the tree at the next iteration. Also, one of the ways that we know this is because we have proven that if a minimum cost path has, let's say, 7 edges, then that path will be in the tree after 7 iterations of the loop. And in general, the proof of correctness in general was if a minimum cost path happens to contain k edges, we are guaranteed that that path will be in the tree by the end of k iterations of the outer loop. Maybe sooner if we're lucky. And basically what we're investigating is how can we assure that we're going to be lucky? Is that something that's easy to do? So, of course, we know that after 3 iterations of the outer loop, this path will be found because it's a path that contains 3 edges. And obviously, that has to be the case. That's why it says obviously here, because the proof of correctness tells us it has to be the case. Were we to find an example that contradicted our proof of correctness, we'd have a whole ton of trouble on our hands. So in general, if I find a minimum cost path containing k-1 edges, so here is a minimum cost path containing 2 edges, suppose that this path, we'll call it P, is the basis of another minimum cost path using 1 more edge. So the path to vertex G is path P with 1 extra edge added to the end of it. Once the algorithm finds path P, we're only 1 iteration away from finding any path that is a single edge extension of path P. And we're guaranteed we'll find that path in the next round of relaxations. So actually what's happening here is I'm slowly developing the theory that actually this whole business about a round of relaxations isn't really the thing I care about. What I care about is once I've gotten a minimum cost path of a certain length, I am only 1 step away, that is 1 edge relaxation away, from finding any minimum cost path that is that path extended by a single edge, whether I do my relaxations in whole rounds across the entire graph or not. Okay, so let's go back to our original labeling of the graph. So the same graph again, but back to our labeling where this thing is now vertex A again. Let's investigate why, if I do 1 round of edge relaxations, everything seems to pan out perfectly in that single round. And as I said a minute ago, my hope here is to figure out that the edge relaxation in rounds strategy isn't really necessary to achieve the effect that I want here. It's not that I have to iterate over all edges to find the path HEDG once I've found the path HED. It's just that I have to hit this one edge. This one relaxation will be sufficient to get me to what I want. Okay, so here's the original graph with original vertex names. The first edge that I consider in alphabetical order is this one, edge AB. Okay, great, so B gets added to my tree. Then I consider edge AC. Now, I want to focus in this case again on the path from vertex, what's now called vertex A, up to what's now called vertex B. These were previously called H and G, but they're the same vertices. So because I only want to focus on that path, I'm going to fast forward a bit. So I just considered the edge AC, and then I'm going to fast forward to right before I consider the next edge along that path. So right before I relax edge CF, the tree looks like this. So I've relaxed edge AB, AC, AD. I've also relaxed edge BC, but it didn't help me. And I'm about to relax edge, I've relaxed edge BE as well. So BE is now in the tree, who cares? But now I'm about to relax edge CF. So what we'll notice here is that at this point, now remember that this is something I'm observing as an outside observer. The algorithm doesn't yet know this, but we know this. At this point, the algorithm has already found a minimum cost path from vertex A to vertex C, which means as soon as it relaxes edge CF, which we happen to know is on the minimum cost path from vertex A to vertex F, as soon as we relax the edge CF, the minimum cost path from vertex A to vertex F will be locked in. It'll be in the tree forever. So I relax edge CF, and sure enough, F is now in the tree with cost 15, which we happen to know from earlier is in fact the minimum cost. And that's how we know that vertex F will never have a lower cost. The cost won't change after this. It's going to stay at this minimum number. Okay, so I just relaxed edge CF. I'm going to fast forward again, because of course the edge CF alphabetically comes before the edge FB. So I'm going to fast forward to right before I relax the edge FB. Okay, that puts the tree in this state here. So notice that as of this point, or actually as of the end of the previous slide, the tree already contains the minimum cost path from vertex A to vertex F. I'm still in the middle of 1 round of edge relaxations here. And then I want to relax the edge FB. So per our observation from earlier, since I already know a minimum cost path from vertex A to vertex F, relaxing this edge, which I know to be on the minimum cost path that gets me to vertex B, will lock in the minimum cost path to vertex B. And so sure enough, there it is. And because this is the minimum cost of travel to vertex B, sure, there could be other ways of getting to vertex B in the same cost, but now that I've found a path with this cost, vertex B's status in the tree will never change. It's going to be in the tree forever, its cost will be 18 forever, and the edges that brought us there will never change. Because the only way the edges could change is if a lower cost path exists, and we happen to know that this is the minimum cost path. Now, just to keep going one more step, so we know that we have a minimum cost path from vertex A to vertex F. So then we go relaxing other edges incident to vertex F. We relax the edge FE. And so that does change the tree a little bit. It doesn't mean, because we weren't talking too much about vertex E here, it could turn out that there is a shorter path to vertex, or sorry, a lower cost path to vertex E via somewhere else. But it's worth considering what we do with this edge. So even if this edge, the edge FE, is not on a minimum cost path from vertex A to vertex E, there might be a lower cost path that gets me to vertex E. Even though it's not on there, once I relax this edge at this step, I never need to relax it again. Because think about what the relaxation logic is actually doing here. The relaxation logic is saying, hey, I want to try getting to vertex E via vertex F. The cost of doing so would be the cost of vertex F, that is 15, plus the cost of the edge I'm using, which is 5. So the total cost I can take is 20. At the next round of relaxations, if I try relaxing this edge again, will anything be any different? Well, of course the answer is no, because the cost of the edge will never change, and the cost of travel to F will never change either. In other words, if I happen to already have knowledge that the total cost of travel to F has been minimized, then I don't need to relax any edges that begin at F ever again, because if I do, nothing will change. I'll just do the same calculation over and over again. Now, the Bellman-Ford algorithm, even though this edge is rejected at this iteration and will never change, the Bellman-Ford algorithm will relax this edge over and over again in every other iteration for all eternity until I found the minimum cost path tree. Even though if this edge is not helpful now, it won't be helpful ever. And even if the edge is helpful now, because you see that the edge actually is being added to the tree, if the edge later gets removed from the tree, which means the edge is not a good choice, the algorithm is going to keep relaxing that edge forever. And that's a sign that the algorithm is doing a lot of work it doesn't need to do. So maybe there is a way that we could refine the logic that chooses which edges to relax to prevent this issue from happening, to remove this duplication. Okay, so basically my observation, summing this up, is once I have found the minimum cost path from vertex A to vertex F, one relaxation of each of the edges that begins at vertex F, edges for which F is the source vertex, will identify any minimum cost paths that pass through vertex F, and no further relaxations of any of those edges will ever be necessary. Because, as I said, if I relax this edge again next time, the calculation I do is the same because it's impossible for the cost of travel to F to ever change. Same thing with this edge, even though this edge may not end up being in the minimum cost path tree. Maybe it gets superseded by some other edge later on. So here's an idea. Instead of relaxing all edges repeatedly, let's only relax edges once I know that the source vertex of the edge has been locked in, that I've already found the minimum cost path to that vertex. So that's an idealized goal. It's hard to know whether I'll be able to implement that in terms of an algorithm, but I think that's the idea I want to go on. I want to take a step back and sum up a few other things about what we've observed with this example, which is that, so what I showed, I guess, like what I was able to see with this graph was that if I visit my edges in a particular order, if I'm lucky enough, for example, with the path that goes AC, CF, FB, if I iterate through my edges in an order such that I see the edges along that path in the same order as they appear on the path, well, then I'm going to get the entire path in just one iteration, because I first lock in AC, then I lock in CF, and then I lock in FB. On the other hand, the other version of the example where I relabeled vertices, I'll use the same labeling for the sake of this discussion, discussion, but in the other version of the example, I considered the equivalent of the edge FB first, and then the edge CF, and then the edge AC. But FB couldn't help me because when I considered it, the cost to F was infinite, so I just ignored it. CF couldn't help me for the same reason, so I ignored it. So the only edge I could lock in after one iteration of the algorithm was edge AC. So there's evidence here that if I consider my edges in the right order, I might be able to lock in a lot of minimum cost paths, maybe all of them, on one iteration of my outer loop. And that's a good observation to carry forward to attempt to build a faster algorithm. Remember, though, that even if that observation holds universally, because all we showed was that it worked on this particular graph, and this was a graph that I constructed for the sake of proving this point. That is, a graph that, was a sort of rigged input to really show off this situation. Even if we could prove that in all cases, for every graph in existence, there is an ordering of edges that results in the outer loop finishing in one iteration, that by itself wouldn't be enough to get a faster algorithm, because we still have to find that ordering. And maybe finding the ordering of edges that works the best takes just as long as the Bellman-Ford algorithm. So of course, what we've seen here, we've come up with a few conjectures, basically. We've observed the way the algorithm works and derived a few suspicions about ways we might speed it up. And I think the best way of encapsulating the idea that we can work forward with is this one. So the case where instead of just relaxing every edge over and over again, we wait until we know that relaxing the edge will be meaningful. In other words, we wait until we know that the source of the edge has been locked in permanently at its minimum cost, and only then relax the edge. If we can do that, and maybe we can't, but if we can do that, then the relaxation only has to happen once. And if we think about that over the course of the entire graph, that means that every edge of the graph only gets relaxed once. If we manage to consider edges in a particular order based on when the vertex that the edge leaves has been locked in at its minimum cost. The question is, can we do that? And if we can do it, can we do it fast? So yeah, the slides are now again late to the party and observing that, yes, if we can figure out a way of implementing that idea, that means I only have to do each edge relaxation once. I just have to be patient and do it at the right time. Okay, so let's just sort of skim over an example of this. We could start by saying, I know that my starting vertex is vertex A here. Okay, so I could begin by only relaxing in my first iteration, instead of relaxing every edge, including edges over here that I know are not going to help me, I could start by only relaxing the edges that leave vertex A, because I could easily argue at the beginning of the algorithm that the minimum cost of travel to vertex A has been locked in at 0. That is, we've already defined the cost of travel from a vertex to itself to be 0. Although there's a bit of an asterisk here that I'll come back to in a few slides, there's something hiding deep down that may not be obvious that we do have to consider, but we'll be able to dismiss it very quickly. If we allow ourselves to assume that the minimum cost of travel from a vertex to itself is always 0, well, then we know that this has already been locked in at 0, and so it's now safe to relax the edges that begin at A. And once I do this once, I will never need to do it again. It's true that the relaxations could be overridden later. So for example, I might discover at this stage that the minimum cost of travel to B is 20, and I set the parent to A. Sure, it is possible that later I set the cost to something lower and give it a different parent. That's fine. What I mean is that the edge AB will never need to be relaxed again. It might be the best contender right now. Even if it's not the best contender later, I'll never have to look at this edge again based on my idea from earlier. Okay, so that means my first iteration only involves relaxing the edges that leave vertex A. So I've already saved a whole bunch of time, a ton of time in general, because we know that the maximum degree of a vertex is at most n-1, where n is the number of vertices. Versus if I iterate over all of the edges, that could be as many as somewhere in the neighborhood of n squared, so n squared over 2, give or take a bit. Okay, so then I've relaxed the edges that begin at A, and then I decide, so this is the place where I'm going to need to write some proofs later, but suppose later I decide, after that first relaxation, that this path here is a minimum cost path from A to C. Okay, why did I fixate on this one? Okay, so I have to be very careful with this. I'm going to come back to this logic in a few slides, but my basic logic is this. Of the various vertices that I can reach right now from A, so there's only 3 of them, B, C, and D, the vertex C has the minimum total cost. And I realize, or I assume, I have to be very careful with this assumption, but basically my assumption is, look, if this were a minimum cost path to vertex B, maybe it is, maybe it isn't, but I'm not yet able to know that, because maybe there's a way of traveling from vertex A to vertex B through vertex C or through vertex D. because I can get to vertex C in a cost of only 13. Maybe there's a way of getting to vertex B from there in a cost of less than 7. So I can't assume this is a minimum cost path to vertex B. I don't know enough to conclude that just yet. Similarly for vertex D, the cost to get to vertex D is 15, but how do I know that there's not some way of getting from vertex C to vertex D in a total cost of 1, which would mean that the total cost of vertex D is actually 14? Conversely, if the cost of going directly from A to C is 13, how else could I get to vertex C? Well, I could take a path that doesn't involve this edge. I could go through vertex B or I could go through vertex D, but to me it looks like that's not going to give me a lower cost path because going through vertex B would cost at least 20. 20 plus something else. And it seems like 13 is always going to beat that number. Similarly, traveling through vertex D would cost at least 15 plus something else. So it seems to me as if 13 will always beat that number as well. There is a huge flaw, a gaping flaw in my logic that I'll come back to in a few slides, but intuitively, that's the logic I want to employ here. Okay, so suppose that I now conclude that the minimum cost path from vertex A to vertex C has been locked in, that there's no way to get to vertex C with lower cost than this. Observe that although I just said my logic was flawed, actually in this case I'm right. It turns out there is no lower cost path to vertex C. You'll see why, despite the flaw in my logic, I'm correct in this case in a few slides. There's actually a property of the graph that tells us that my assumption turns out to be correct here. Okay, so because of that, I can conclude that since I've locked in vertex C, since it's already at its minimum cost, it is now safe to relax the edges that begin at vertex C. So I do that. Okay, so I relax the edges beginning at vertex C, and now I stare at the result, and again I observe that if I consider the minimum cost of travel to different vertices, okay, well so now vertex F costs 15 and vertex G costs 17. And you can see I can sort of proceed on the same logic. I could say, well, okay, I still don't know that vertex B is at its minimum cost, because for all I know, there's a path from vertex F to vertex B, where it costs 15 to get to F and maybe, 1 or 2 more to get to B. So vertex B is not yet ready to process. Maybe there's a lower cost way to get to vertex B. On the other hand, by my logic, it does seem as if maybe there is no faster way, there is no lower cost way to get to vertex D, or a lower cost way to get to vertex F, because every other vertex I could travel through would have total cost greater than the current cost of a path that I know to vertex D or vertex F. So suppose, because vertex D and vertex F are tied, they both have 15, suppose I choose vertex D here. Okay, so I choose vertex D, and I say, hey, okay, it looks as if vertex D can be locked in. There is no lower cost path to vertex D. There are other ways I can conclude this. So one other way is observing that there are no other inbound neighbors to vertex D. There's actually no other way to get to vertex D. Even without that more semantic observation, it's worth observing that even if we allow there to be the possibility that some edge into vertex D exists from some vertex I haven't thought about yet, to getting to that edge would require a total cost of greater than 15, because I'd have to travel through, let's say, vertex G, or vertex B, or vertex F. Okay, so I conclude, therefore, that the edge AD is a minimum cost AD path. Okay, so I then relax the edges connecting D to its neighbors. In this case, nothing changes, I think, because it turns out that we know that vertex C is already minimized, and I think vertex G, we can get to vertex G faster or with lower cost via vertex C. Now at this point, because I've locked in vertex A, vertex C, and vertex D, I could say those are never going to change. The structure of the tree as it applies to these 3 vertices is locked in permanently. Let's just circle them in green to indicate that that part is never going to change again. And the rest of the tree, so these edges here, might change. I might discover edges that supersede these ones, but the ones inside the green outline are locked in forever. And I also observe that if over time I can get the green outlined region to grow to encompass the entire graph, that would tell me that I've locked in the entire graph and I'm done. And I think for a minute and realize, hey, wait a minute, I'm growing a tree here. I've got this green outline that's supposed to grow to encompass the graph. Somehow I'm getting a bit of a sense of déjà vu from this. This looks a lot like Jarnik's algorithm. So the procedure I've just outlined of starting at vertex A, starting at our starting vertex, and slowly growing my tree outwards and locking in certain portions of my tree as I go until the locked-in portion encompasses the entire graph, that is eerily similar to Jarnik's algorithm for minimum weight spanning trees. And I observed at the beginning that there are some superficial similarities between the minimum weight spanning tree problem and this one, so I suppose it can't be too surprising that this looks like Jarnik's algorithm. Okay, so I guess we now have a new focus for our attempt at developing a faster algorithm. Can we adapt Jarnik's algorithm to solve the minimum cost path problem? For the sake of my illustration, I would like to explore the graph sort of like how Jarnik's algorithm does. That is, when we work with Jarnik's algorithm, we don't care about what's happening really far away from our tree. So to try and simulate that exploratory process on slides, what I've chosen to do is to obscure the weights of all of the edges in the graph that aren't immediately touching my tree, because I shouldn't know what they are because I'm only focusing on my tree. That's what's going to make the algorithm fast, that I only work on my tree and expanding my tree outwards by one vertex at each step. Okay, so for example, suppose that I start with vertex A as my starting point. I add it to my tree. The tree now contains one vertex, my starting point vertex A, and the only edges I'm allowed to consider are the ones that immediately leave vertex A. Okay, so I can get to vertex B and cost 100, vertex C and cost 100, or to vertex D and cost 10. And now the question is there a clear choice of vertex to lock in? And I would like to believe, I've got to be very careful here, but I would like to believe that the answer is, well, yes, it's D. Because I think, okay, I can get to vertex D through a path of cost 10. Now, suppose there was some other way to get to vertex D. Well, it wouldn't involve the edge AD, obviously, so it must involve either the edge AB or the edge AC. Now, suppose for the sake of argument that I don't know anything about the other edges, like where they connect to or how many other vertices there are. In that case, a path to vertex D via vertex B, well, it seems to me like that would have to cost at least 100, because the edge to get me to B is 100. Similarly, a path to vertex D via vertex C would have to cost at least 100. And neither of those could outperform this edge, which has cost 10. Okay, so from this point of view, based on what I currently know, it looks like edge AD provides a lower cost path than any other option, because any other option must go through these edges of cost 100. So I guess that means I can lock in vertex D. The minimum cost of travel to vertex D is 10. We're good. I've just expanded my tree by one vertex. And if I can keep expanding my tree by one vertex, eventually I will have solved the problem. But it turns out there's a problem. So it turns out that elsewhere in the graph, far away from my starting point, and we could make this arbitrarily far away if we wanted to, so thousands of vertices away if we wanted to, there's this edge. This edge has weight -200, which means, yes, it does cost a lot of money to travel to vertex B. But once I get to vertex B, somebody writes me a check for $200 to go to vertex F. So by the time I get to vertex F, I have actually made $100. And if I then travel onward to vertex D for the low cost of $3, it means there is a path to vertex D that pays me $97, with total cost -97, which of course is way better than what I thought was the best path, the path of cost 10. So the assumption I just made turned out to be completely wrong. It actually turns out that the minimum cost path from vertex A to vertex D doesn't involve this edge at all. Okay, so what do I do? Do I give up? Well, maybe I do. Maybe this is so disheartening that I just go do something else. On the other hand, we're only at slide 43, and we all know by now that lectures can't be that short, so I guess I should push on and try and fix the issue. So what I would like to observe here, and I think it's pretty easy to justify this, is that the only reason that my assumption was wrong was that somewhere else in the graph there was an edge with negative weight. Now, I made a big deal in the last lecture. I went to great pains to emphasize that negative weight edges are fine. There is nothing inherently wrong with them. However, it is true that they can be troublemakers. That is, we already saw that without negative weight edges, you wouldn't have negative cost cycles, and negative cost cycles are a bit of a problem. And it turns out here that this negative weight edge is becoming a bit of a troublemaker. Because if this negative weight edge weren't here, if I were guaranteed that all edges had positive weight, if you guaranteed me that absolutely, then the assumption I made earlier would hold perfectly. So if I know that no edges have negative weight, then there is no way that I could turn a path that began with the edge AB into a path of total cost less than 10. It would be impossible, because how do you add a bunch of non-negative numbers to 100 to get a number less than 10? It's not going to happen. Same thing with the path through AC. The only reason why my assumption didn't hold was that there was a negative weight edge in the graph. So that's the claim I want to make. We could even write a proof of that claim, but I believe that the claim is reasonably self-evident. It comes down to properties of arithmetic. The fact that if you have no negative signs anywhere in the graph, there is no way to make a path whose current cost is cost 100 cost any less. There's no way of bringing that cost down because the cost can only get larger over time. Now, Again, negative weight edges are no big deal. They should be allowed to exist. There are plenty of valid interpretations of this problem where negative weight edges can and should exist and need to exist for the problem to be modeled successfully. And the reason I take such great pains to say that is because, as I mentioned last time, a lot of sources will describe this whole problem, what I'm calling the minimum cost path problem, as the so-called shortest path problem, which adopts a sort of default interpretation of the weights as being distances. And that means that there are people out there taking algorithms courses that learn about the problem in terms of the distance interpretation only. And although certainly they later learn about the Bellman-Ford algorithm and negative weights, they might develop superstitions that negative weights are bad, or that we shouldn't have negative weights, or even that we can't have negative weights, which are all wrong. Negative weights are fine, however, they do make our life a little bit harder sometimes. And we need to make sure that we don't develop a bias that negative weights are somehow bad. It's possible that one day you are working on a problem where you're modeling something with an edge-weighted graph and you have negative weights, and you think to yourself, it would be great if I could get rid of the negative weights so I could use a faster algorithm than Bellman-Ford. That is a healthy approach to this. But I don't want you ending up in a position where you think, uh-oh, I've got negative weights, therefore I have no idea what I'm doing and the problem is a failure. Well, no, negative weights are fine. They are not inherently problematic, although yes, they do cause all sorts of mischief in certain contexts. So how about this? I want to try and save my earlier observations. I want to try and build a faster algorithm even if it requires me to restrict my input cases a little bit. So what if we require that edge weights are always non-negative? Because my observations do not hold up otherwise. The key thing I wanted to leverage, that is the fact that this is guaranteed to be a minimum cost path looking only at the neighbors of vertex A, that isn't going to hold up if there are negative weight edges hiding literally anywhere in the graph. Now it turns out that it would be fine if the negative weight edges were somewhere that would be harmless. So if this were negative and this weren't, well, it turns out that's not going to hurt anything because vertex E can't help us for a path to D. But it could be a problem for some other vertex, and so one way to avoid having to give up and still work around this problem is to say, how about this? Let's assume that there simply are no negative edge weights anywhere. So we're going to assume that all edge weights in the graph are non-negative. They can be zero, they can be positive, but they can't be negative. In that case, the assumption that I made earlier does hold, and also in that case, it is a bit more natural to talk about this as the shortest path problem. If we know that edge weights are non-negative, then the distance-based interpretation does hold up quite a bit better. That is, we no longer have to worry about this weird situation of there being a negative distance, which makes no physical sense. And so this is much more natural if we wanted to talk about the minimum cost path problem in terms of distances and call it the shortest path problem. And as I said, many sources do that. That's how they present this problem, as the shortest path problem where the edge weights represent distances. And that's fine. They're welcome to do that. And when you have no negative edge weights, that modeling, it makes more sense. It's more natural. There are lots of sources that cover it and call it the shortest path problem, even when they talk about negative edge weights, which is fine too. It just feels like that's just a bit of extra mental work to try and remember that, yes, negative edge weights don't literally mean negative distances. That's a matter of the modeling. I'm going to keep talking about this in terms of minimum cost paths, even though at this point we could just switch over and adopt only the shortest path and distance interpretation. The reason I'm going to stick with the cost modeling is I like it, and it's consistent with the previous lecture, but also because I'm very wary of the words distance and length having multiple meanings. Because the formal, and there's nothing wrong with this in general, like I do work with shortest path problems outside of teaching this course, obviously. But I think as far as trying to internalize the problem, it's nice to not have words that have two meanings. So for example, if I talk about a path, here's a path here. So A to D, D to G, and then G to H, for example. If I talk about the length of a path in an arbitrary graph theoretic setting, the length of the path is the number of edges on the path, so 3. If I talk about the distance from vertex A to vertex H in a graph, in an arbitrary graph, especially one with no edge weights, the graph theoretic distance between two vertices is the number of edges on the path with the fewest edges, so the minimum length of a path. Those already have well-defined meanings, so it feels to me like we're just going to be confusing things by talking about shortest paths, because shortest paths could mean something like a path with the fewest edges. I brought this up at the beginning of the last lecture as well. That's one reason I like to stick with the cost interpretation. Okay, so now that I'm assuming that there are no negative edge weights, even if I only consider the immediate neighbors of vertex A, and I literally know nothing about the other weights in the graph, then it is actually reasonable that in this case, so if we look at these in this graph here, edge AB, that edge AB is and has to be a minimum cost path from vertex A to vertex B. And the reason for that is pretty simple. If there were a path that had lower cost, then that path would have to pass through either the edge AC or the edge AD. But both of those edges have a higher cost than 10. If the graph contains no negative edge weights, how can I begin by paying $30 and end up eventually back at vertex B having paid less than $10? That doesn't make any sense. And so at this point, because I have no negative edge weights, this observation does hold up. And I can now try and use this observation to extend Jarnik's algorithm to the minimum cost path problem. Okay, so I lock in the path from vertex A to vertex B along edge AB as a minimum cost path. And then the question is, okay, what vertex do I bring in next? To do this, what I have to consider is the total cost of travel to all vertices that are within one step of my tree. For example, I can reach vertex, let's do vertex E first. I can reach vertex E via vertex B for a total cost of 20. Okay, I can reach vertex F via vertex B for a total cost of 30. I can reach vertex C via vertex A for a total cost of 30, but then I also realized that I could reach vertex C via vertex B for a total cost of 15. Okay, so 15 clearly is the better number. We'll keep that one. I can reach vertex D via vertex A for a total cost of 20, and I think that's it as far as being one step away from the tree. Okay, so I apply the same logic again, which is, well, the current cost of travel to vertex E is 20, but how do I know that there's not some way of getting to vertex E, let's say, via vertex C? And if I go through vertex C, maybe there's a path from vertex C to E that has cost 1. Okay, so that means vertex E shouldn't be brought in just yet. Maybe I haven't found the minimum cost path to vertex E. On the other hand, vertex C has total cost 15. And it doesn't look like I can do better than that, because any other path to vertex C would have to pass through one of these vertices here, all of which have total cost greater than 15. Okay, so I then bring in vertex C. And that means that the path that I found to vertex C, the one that goes through vertex B, which is the lowest cost way to reach vertex C through the tree vertices, that must be a minimum cost AC path. Okay, I bring that into the tree. And hopefully it's already clear that as long as I can keep this up without getting stuck, as long as I can keep this up, I will find my minimum cost path tree. If I can just keep expanding my tree by one vertex at each step, it eventually will contain everything reachable from my starting point. Okay, so if I don't want to skip to that step just yet. If I now recompute the minimum cost of travel to various places, okay, I can still reach vertex E and cost 20. I can reach vertex F via vertex B with cost 30. I can reach vertex F via vertex C with cost, so remember that the cost of travel to vertex C is 15. I can actually reach vertex F for total cost 21. I can reach vertex D by cost 20 from A, or by cost 42 from C. Okay, so obviously I just want to keep the edge from A. And so I realized that at this point, of the non-tree vertices I can get to in one step, the cheapest ones are either D or E. Okay, so I guess to break the tie, we'll choose the alphabetically lowest. Let's choose vertex D. Okay, so the best way to get to vertex D is via the edge AD, so I bring the edge AD into my tree. And what we're observing here, so as with every previous case, what I'm pointing out is that there is no faster way or no lower cost way to get to vertex D. Even if there were a path that went through these edges that I do not know the weight of, notice that getting to vertex F costs 21. And so even though I don't know the weights of these edges at all, they pass through an uncharted region of my graph, there is no way that the weights of those edges could lead me to a total cost that's 19 or less. It's impossible. So I know that this has to be a minimum cost path. Okay, so I can bring that into the tree. Now, really all I've done here is Jarnik's algorithm, with the only real change being that, just like Jarnik's algorithm, I bring in one edge at a time. So I sort of haul in one extra vertex by pulling it in via some specific edge, although I guess the edge I used here was this one. The difference between Jarnik's algorithm and this one is, with Jarnik's algorithm, all I care about is the weight of the edge that I'm bringing in. I just bring in the edge, the lowest cost edge attached to my current tree. With this this algorithm, I'm not considering just the weight of that edge, but the total cost of travel from my source vertex to the destination. So instead of just considering the number 6, I'm considering the number 15 plus 6, the cost of travel to C plus the cost of taking the edge itself. Otherwise, I'm pretty much looking at Jarnik's algorithm. The resulting algorithm, the minimum cost path extension of Jarnik's algorithm, is called Dijkstra's algorithm. Now, back when we talked about Jarnik's algorithm, we had to go through this whole history lesson to try and figure out who to name the algorithm after. Recall that it was invented by Jarnik in 1930 or so, and then 27 years later, it was rediscovered by Prim, and because the people that wrote algorithms textbooks in English were more likely to have read Prim's paper, I guess, it ended up being named Prim's algorithm for a very long time, including to this day, like the Wikipedia article about that algorithm is titled Prim's algorithm. Later sources, once Jarnik's contribution was recognized, called it things like the Prim-Jarnik algorithm, which is a cop-out, because if you acknowledge that Jarnik invented it, you should call it Jarnik's algorithm. And there was this weird case where a couple of years after Prim, Dijkstra showed up and claimed to have reinvented the algorithm again. Now, that may have been the case, but it's sort of weird to say that even though 2 other people have already invented it, they should put Dijkstra's name on it as well. And so I strongly disagree with the argument that we should have called Jarnik's algorithm the Jarnik-Prim-Dijkstra algorithm. That didn't make any sense to me. On the other hand, Dijkstra did invent this minimum cost path algorithm. It's very similar to Jarnik's algorithm, but it is distinct. And Dijkstra did invent it, and there is no controversy about that. So Dijkstra was a very famous computer scientist, and one of the things for which he is the most famous is this algorithm. This algorithm is a pretty big deal, and he did invent it, and there's no controversy about that, so we are going to call it Dijkstra's algorithm. Okay, let's try it out. Now, one thing you probably noticed during that last example was that I was spending quite a bit of time at each step recomputing the total cost to reach each vertex. Obviously, I don't need to do that because just like with the Bellman-Ford algorithm, I could just be keeping track of the current cost of travel to each vertex in a table. Similarly to how I could be keeping track of the current tree or the current set of edges that I'm keeping track of, whether they're in the tree, the locked-in part of the tree or not. I should clarify that. Basically, I might want to keep track of that the current cost of travel to vertex E is 20, but that comes in along this edge here. So like Jarnik's algorithm, I can use a parent array to sort of keep track of the tree neighbor of vertices that aren't currently in the tree and the tree edges for vertices that are currently in the tree. So I'll use this table for that. Let's just try running Dijkstra's algorithm. We sort of already know what it does, so before seeing pseudocode, we actually can just try running it on this example. Let's start with running it with our start vertex being vertex A. Okay, so similar to the Bellman-Ford algorithm, I have to keep track of the best known path and the current cost of travel. But also, because the minimum cost path tree is a tree, I can keep track of the best known path to a particular vertex simply with a parent array. I could then recover the best known path. If I know that the parent of C is B and the parent of B is A, I can recover the path using the tree itself. All right, and then I will also use the parent array to refer to vertices that are not in the tree but are one step away. As I mentioned a minute ago, for example, if my tree currently consists of these 3 vertices, vertex E is within 1 step, so the cost of travel to E might be currently 20, and the parent might be B. The idea being if I bring vertex E into the tree at this step, I'd be bringing it in along the edge of BE. So we're only going to add a vertex to our formal tree once I've found the minimum cost path. And after that point, so once I've added it to the tree, the information in the table for that vertex is locked in permanently. Because once the cost is the minimum cost, it's never going to go down further. And the cost, of course, never goes up, just like in the Bellman-Ford algorithm. Now, in the visualization, I'm going to use the green outlining to show what's currently in the tree. I will also fully shade table entries for tree vertices green to indicate that they are locked in forever because the vertex is in the tree. Okay, so we start off by adding our start vertex, vertex A, to our tree. We then relax the edges corresponding to neighbors of the vertex we just added, so edge AB, AC, and AD. I relax them, I update the table correspondingly, so I now know that the cost of travel to vertex B, the best cost I know of so far is 10, the cost to C is 30, the cost to D is 20, and each of them come in via the edge from A, because A is the only tree vertex that exists. Okay, so after we've initialized the algorithm, we just perform a sequence of iterations. At each iteration, we bring in one vertex, and what we do is just choose the non-tree vertex in the table that has the lowest cost. So in this case, that would be vertex B. There's a secondary case I'll come to later, which relates to an infeasible path or in a graph where not all vertices are reachable from the starting point. I'll come back to that. There's a little bit of an extra nuance we'll add to this condition at that point. Okay, step 1. At this point, the non-tree vertex with the lowest cost is vertex B. So I add the edge. Well, the edge that I want to add is the edge between this and this, so A to B. So I add that edge to the tree. Okay, and then I bring vertex B in. Vertex B gets locked in. I then relax the edges from B to each of its outbound neighbors, and this results in me updating the table. So the cost of travel to C is now 15 along the edge BC. The cost of travel to E and F are now 20 and 30 respectively. And then I'm done my iteration, and so I go looking for the next one, and then it turns out there's a slide with some pseudocode in the middle. Okay, so I just talked about how after we add a vertex, we relax the edges to its outbound neighbors. I'll just show off the pseudocode for that. Really what I'm doing is this. So I've just chosen a vertex U to add to my tree, and I just do the same edge relaxation procedure I did with the Bellman-Ford algorithm. That's it. Like when I say edge relaxation in these slides, whether I'm talking about the Bellman-Ford algorithm or this one, I mean literally the same thing. I just mean this if statement, check whether this edge that I'm relaxing provides a better path, and if so, update the table correspondingly. Okay, so as I mentioned a minute ago, once I've added vertex U to the tree, these two values will never change again, because there will never be a lower cost path than the minimum cost path, and I only update the parent value when I find a lower cost path. So I'm actually going to say this multiple times, because it's really important that we keep this invariant in mind for our proof of correctness. Okay, anyway, where was I? So at this point, after I've locked in vertex B, the non-tree vertex with the lowest cost would be vertex C. So I bring in edge BC and I add C to the tree, and then I relax the edges to the neighbors of C. So that would be edge CF and edge CD. Notice that so far, my earlier assumption that I would be able to do this by relaxing every edge only once has held up. I relax the edge, each edge gets relaxed when I add the source vertex for that edge to the tree, and it doesn't get relaxed at any other time. Okay, so anyway, I relax the edges corresponding to neighbors of C. Those edges are the edge CD, but I observe that if I use the edge CD, the total cost is 27, which is greater than 20, so vertex D doesn't change in the table. On the other hand, I believe the previous cost to F was 30, but if I come in via vertex C, it's 21, so F gets updated in the table. All right, step 3, the non-tree vertex with lowest cost is vertex D. Okay, so I bring in edge AD, and then I relax the edges for neighbors. That would be edge DG. So I now have a better way to get to, actually I now have any way to get to vertex G. Great. Now the non-tree vertex with lowest cost is edge E. So I bring in vertex E. And now for the first time over the course of the algorithm, every vertex is somehow reachable. Although I don't necessarily have the minimum cost path to these vertices yet, we are definitely making progress towards having the solution that we're looking for. Okay, so then I bring in a vertex F and relax edges to its neighbors. That doesn't seem to change anything. And then I relax then I bring in vertex G, relax edges to its neighbors, and then finally I bring in vertex H. Okay, so I've clearly reached a termination condition. You'll notice that the slide is written something more complicated than what I seem to need here. In this case, I can observe that my tree now contains every vertex, and therefore that there's nothing left to add, and so the algorithm is now done. The slide phrases it in a more complicated way. It says something about non-infinite costs. I want to show off a case where we do need a more complicated condition, because it turns out that here we were lucky that everything in the graph is reachable from vertex A, but that's not always the case. If we only terminate the algorithm once everything in the graph is contained inside the tree, we could find ourselves in trouble in certain cases, specifically if we reach an infeasible case. So we're going to try it again. Same graph, but this time I want vertex E to be my starting vertex. And so, I can use any vertex I want as my starting vertex. The observation I want to make is that there are clearly vertices in this graph that are not reachable from vertex E. So for example, nobody can get to vertex A. Vertex A only has outbound neighbors. All right, so I initialize by relaxing the edges to neighbors of vertex E, so I get this initial table, and then I just walk through the algorithm again. So the non-tree vertex with lowest cost is vertex H, so I bring vertex H in and relax its neighbors. And then I bring in vertex F, and then I bring in vertex G, and then I bring in vertex D. Hold on. And then actually I'm done. Even I went too far there. Even I lost that the algorithm actually has to stop at this point. So after I brought in vertex D, the only neighbor vertex D has is G, which is already in the tree. And I realized that after I brought in vertex D, I actually haven't reached any of these vertices yet. So the tree does not contain everything in the graph, but the algorithm has to be finished because there's no way to reach vertex A, vertex B, or vertex C. At the current state of the algorithm, the cost of travel to all three of these vertices is infinite because there is no way to reach them. And if you stare at it for a bit, what you'll realize is that I can sort of cut the graph here, and all edges go this way across the border. There is no way to get from this segment of the graph back into this one. And that means that the problem of what is the minimum cost path from vertex E to vertex A, that's infeasible. There is no path from vertex E to vertex A. So the real termination condition of the algorithm is when you reach a state when there are no non-tree vertices with non-infinite cost, the algorithm must terminate. So here, there are non-tree vertices, but they have infinite cost, so the algorithm terminates. Back in our earlier example, if I scroll all the way back to that, here, if I look at all the non-tree vertices with non-infinite cost, well, there are none, so the algorithm can terminate here as well, because there actually are no non-tree vertices left. But I need both of those conditions to be working together in this, because there could be cases where vertices do not get reached at all. Okay, now we're ready for some pseudocode. Here is basic pseudocode for Dijkstra's algorithm. Now, it's basic because I'm going to see in a minute there's a place I might want to speed it up, but it's sufficient to prove its correctness. That is, we have enough here to state the algorithm formally so we can prove it's correct, and then go around doing running time optimizations afterwards. So what I do is I'm going to curate a set of tree vertices. Now, like with Jarnik's algorithm in the minimum weight spanning tree lecture, to be honest, this implementation might be a little bit bulky. It is not any slower than any other implementation, given the choices I've made, but I might be storing more data than I need for the sake of convenience. So I keep a set of tree vertices, and then I'm going to use this loop to iterate until the number of tree vertices equals the number of vertices of the graph. So the primary termination condition is if I reach a state where everything in the graph is in the tree, then I'm done. But of course, I could have to terminate earlier. This loop by itself would become an infinite loop if I reach a situation where I can no longer add vertices to the tree. So I have a secondary condition. At each step, I go grab the vertex, which is the non-tree vertex with minimum cost, and then, if it turns out that no such vertex exists except for one with infinite cost, so if the only non-tree vertices have infinite costs, then I break the loop. Then the algorithm has to terminate because I can't expand the tree any further. So between these two conditions, the loop condition and this extra early condition to bail out of the loop, these enforce the termination condition I described a minute ago. So otherwise, I have a situation where the vertex u that I just went to find is a non-tree vertex with non-infinite cost, and it has the lowest cost among all such non-tree vertices. I add it to my tree, and then I just relax. This is the same loop as I would have in the Bellman-Ford algorithm, but specialized to the neighbors of one particular vertex. I just relax the edges that leave that vertex. And I hope that when you look at it, you observe that it's sort of a fusion of Jarnik's algorithm, that is the overarching logic, and the Bellman-Ford algorithm, which is the edge relaxation logic. And then this version returns a parent array, and of course you could use the parent array to reconstruct the paths in the tree. I don't know if I buy this wording. It can be used to reconstruct the tree. The parent array is the tree, so I feel like this isn't fair to the parent array, but it certainly can be used to reconstruct the paths in the tree, just like the Bellman-Ford pseudocode. If you want a particular path, you could go extract it from the tree in time proportional to the length of that path pretty easily. So there are other ways of framing this, but returning a parent array is a nice general way of doing it, I think. All right, so the running time of the outer loop in the worst case is pretty obvious. It's going to be the number of vertices, so size of v. Okay, so there's that. And then the question is how much work actually gets done inside the outer loop. And it's pretty easy to argue that this stuff can be done in constant time, as can this stuff here. So really the only two unknowns are line 7 and this loop here. Now, fortunately for us, we're actually quite used. There's logic we can use that we've used for many other algorithms that allows us to get a handle on the running time of this inner loop and avoid some annoying summation, which is pretty much that we can argue that each vertex gets added to the tree exactly once at most. It'll never be added to the tree twice for the following reason. The vertex u that I add to the tree at line 11 is chosen to be a non-tree vertex, which means the only time I ever add a vertex to the tree is if it wasn't in the tree already. So every vertex can be added at most once. Okay, that's great, which means basically that for a particular vertex u, this loop only gets executed once for each vertex u. And also that if I consider the number of edges in the graph, well, what I'm doing here is iterating over all the edges that begin at a particular vertex u. And in the worst case, I will do that for every possible vertex u, which means if I consider the number of iterations of this loop over all iterations of the outer loop, it can be at most this number of edges, because each edge will be seen exactly once. As I observed earlier, that was the goal we were trying to enforce, that I relax every edge only once over the entire course of the algorithm. So this is similar to what we did when we analyzed Jarnik's algorithm, which is why I'm talking about it at a pretty high level. Over all iterations of the outer loop, the inner loop considers each edge only once. And then there's line 7, which is just vague. So we don't explain exactly how we do this. For the sake of pinning down the algorithm with any running time, let's just assume that we do this in the most obvious way. If I say, give me the non-tree vertex with minimum cost, you could just go do linear search over the cost array. Just go look at everything in the cost array and find me a vertex that isn't in the tree and has minimum cost among all vertices not in the tree. Suppose that I therefore do line 7 with linear search. Well, the size of the cost array is number of vertices, and the number of iterations of my outer loop is also the number of vertices. And then this, over all iterations of my outer loop, is going to have this running time, which means the total running time overall is going to be, well, it's going to be v squared all plus e. And then, of course, we know that e is at most v squared in the worst case, which means this is actually just going to be big theta of v all squared, which isn't bad. That's definitely that's a concrete improvement over the Bellman-Ford algorithm. The Bellman-Ford algorithm could be v cubed in certain cases. And so this one, we get it down just to v squared. You can think about cases where the running time of Bellman-Ford is v times e. Mull over the fact that there are certain cases based on the value of e where the Bellman-Ford algorithm can be faster than v squared if the number of edges is incredibly small. If that's the case, if the number of edges is less than the number of vertices, well, then you can expect this will be less than v squared. On the other hand, you can also expect that the number of reachable vertices from a particular starting point has to be sort of low because the graph can't be connected at that point. Now, we know already that Jarnik's algorithm, which this is extremely similar to, can be optimized by choosing better data structures that help us do this. This seems to be the bottleneck. Everything else, that is the fact that we may have to iterate v times here, well, that makes sense. Our tree could actually contain v things. And the fact that this iterates overall every edge in the graph once, well, that also makes sense because I should consider every edge before making any pronouncements about minimum costs. So I know there's going to be a v and an e. The question is, do I really need to spend big theta of v time finding the non-tree vertex with minimum cost? And so like Jarnik's algorithm, there are ways to optimize this, and we should employ those optimizations here, because it's pretty easy to see that if we look at how, which parts of this stem from Jarnik's algorithm, which parts stem from Bellman-Ford, they don't really mix together that much. So that is the Bellman-Ford contribution, the minimum cost path aspect, is actually just this stuff. Everything else is pretty much an implementation of Jarnik, except I guess this condition is sort of bizarre for Jarnik's algorithm, but it doesn't really change much, which does tell us pretty much that if I do the same optimization process as I did with Jarnik's algorithm, I should get the same speed up. But before we do that, let's prove the correctness of what we have. That is, this is sufficient. This is in enough detail that we can write a proof of correctness. Let's get that out of the way. So what I'm going to prove is that when a vertex v is added to the tree, the value in the array cost v is the true minimum cost of a path from the starting point to vertex v. It is sufficient only to prove that. And the reason, if we wanted to write a justification of why I don't need to prove anything else, the summary would basically run like this. Cost v, if we look at the pseudocode, cost v only gets changed when it could get smaller. So observe that when I modify cost v, that would be here. The only time I ever modify the cost of travel to a vertex is here, other than when I initialize it to infinity at the beginning, or set the cost of the travel to the initial vertex. The only time I ever modify it in the algorithm is this line here. And when I change it, it explicitly, based on the relaxation condition, must be changed to a value that's smaller than what it is already. The change only happens if the new value is less than the old value. Okay, so that's one observation. The next one is, what that basically tells us is, if cost v is the true minimum cost of a path, there is no way the algorithm will ever make it any smaller, because a secondary thing that I'll talk about in a minute, which is to justify that the tree that the algorithm is computing actually is a minimum cost path tree, sort of tells us that as long as the costs that the algorithm are setting are based on real paths in the graph, in other words, I only set the cost of let's call this vertex Q. I only set the cost of travel from vertex Q to vertex V to be 10 if there actually exists a path of cost 10. As long as that's the case, and I think it's pretty easy to argue that that's the case here, that is that the algorithm is legitimately using the costs of real paths to set the cost values in the array. As long as that's the case, then cost of V will never go down as long as it's already hit its minimum value, obviously, because it can only go down if you find a lower cost path, and the algorithm can't find a lower cost path than the minimum cost path. Now, before I do the proof that proves this fact, I will also observe one other contingency that maybe somebody cares about, is that, yeah, hold on a minute, how can we be absolutely sure that the tree that the parent array contains actually contains paths whose costs equal the costs in the cost array? I know that sounds like word salad. In a sense, that's sort of a justification for why I don't feel the need to prove it, because maybe it's self-evident, but if not, there is a way of writing a sort of tedious proof of this fact. Basically, what I'm saying is that if we discover that cost of V equals, let's say, 10, what I'm relying on here is that we can, by looking at the algorithm and understanding how it works, it should be reasonably clear that the only time I ever set the cost value of a vertex is when I physically found a path of that cost. And that means I should assume that if I look, suppose again that the path was Q to vertex U to vertex V, that if I trace through the parent array to find the path that ends at vertex V, that path actually does have to have cost 10. Maybe I need a proof of that fact. I'm going to treat that fact as being true. If you want to write a proof of it, you'd find it wasn't difficult. You could do it with a variety of methods. Maybe you could use a loop invariant or something. But I regard that as something that we can see, basically, if we observe that the parent array and the cost array are always updated in lockstep. So the only time I ever update the parent array is when I'm also updating the cost array at the same time, and the updates are proportional, I guess. That is to say, the update I do to the cost array is based on the same modification I'm performing to the parent array. So I am acknowledging that this is not something I'm writing a formal proof of, but I believe it to be something that somebody who reads the algorithm could accept with little other justification beyond simply stating this fact. If you wanted a proof, though, you could write one. Now, the main proof I want to write here, which is this theorem, which is in a graph that has no negative weight edges, at the moment when Dijkstra's algorithm adds a particular vertex to the tree, the cost in the cost array for that vertex is the minimum cost of that path. I want to prove this theorem. The proof I'm going to write is not my own proof. It is a proof from the CLRS book. Now, it's actually weird seeing the real name of that book. The real name of that book is Introduction to Algorithms, which is such a vague name that people just call the book CLRS. It's a book with which you are likely very familiar by now. The proof that I am writing here is basically just that proof. I've made a couple of adjustments to it. Most of my adjustments are to make it easier to put it on slides versus to write it down. I use a tiny bit of different notation to be more consistent to other notation we've used in this course and to avoid creating confusion. And I have made one non-trivial modification, which is that the proof in the book is a proof by contradiction. I have chosen to structure it as a proof by induction. Now, this is just a matter of personal taste, and if you're interested in looking at both versions, try comparing them side by side. I'll bet you'll agree that the logic is pretty much the same. It's just the order in which things are presented. I mentioned in an earlier lecture that in my background in some abstract algebra course I took a very long time ago, the instructor said one day, you can always write proofs of contradiction for things, but if you can find a way to not use a proof by contradiction, do it. If there's a way of writing a straightforward proof, a sort of positive proof, I guess, write that proof instead. And that was just their opinion, frankly, but I took that to heart quite a bit, and I feel like although proofs by contradiction can often be quite clever, and if you have a way of writing a proof by contradiction that's more compact or more clever, that is a good argument in favor of writing it. But there is something about proofs by contradiction that although they prove the thing you're trying to prove, they don't give you as much of a flavor for why the thing is true. They sort of tell you why the thing can't not be true, as opposed to telling you why it is. And so in this case, because both it works better on slides and because it feels like a better emphasis of why something has to be true, I've chosen to adapt the proof to use induction. So any mistakes in the conversion to an induction proof, I take responsibility for those. And also that the proof itself, I do not take credit for. That was somebody else's work. It is a really nice proof, which is why I chose to adapt that rather than try and muddle through creating my own proof from scratch. Now, in the proof, I want to differentiate between what the algorithm thinks the minimum cost is, which would be the value in the cost array, and what the real minimum cost is. So I'm going to use this notation, capital M of 2 vertices, so I'll write it in the abstract sense. If I write M of UV, I'm talking about the minimum cost, the true minimum cost of a path from vertex U to vertex V. So the algorithm doesn't know this information. I'm trying to prove that the algorithm is able to figure this out. So M is the true minimum cost. And what I'm going to be arguing is if we number the vertices in the order, we use a numbering corresponding to the order in which they are added to the tree, then when I add vertex Vi to the tree, the cost in the cost array is the true minimum cost of travel to that vertex. Okay, so more on the numbering scheme. Let's let Vi be the vertex added to the tree at iteration I of the outer loop. And let's just define that V0, so the thing added before the first iteration, we'll say that's V start. Okay, so V0 is the first vertex added to our tree. It is the start vertex. Okay, so the proof is by induction. The base case is based on V0, and there's a typo right off the bat. Sorry about that. This should say V0, obviously. So when I equals 0, well, then that's when I add vertex V0 to the tree. Now, we have defined earlier that we consider the cost of travel from any vertex, so here's my vertex A, the cost of travel from A to itself, well, I could just stand still and do nothing. If I'm on vertex A, I do nothing. I'm still on vertex A, so I've successfully traveled to vertex A. The cost of travel from a vertex to itself is always 0. So the cost of travel from vertex V start to vertex V start is 0, and so the theorem holds. Now, there's an asterisk I placed earlier in the lecture that I will finally resolve, which is, wait a minute, is it always true that the minimum cost of travel from a vertex to itself is 0? And the answer is, well, actually, maybe not. So maybe it is possible to start at vertex A and go off on a long adventure and come back and have made money. Because, of course, to have a cost better than 0, it has to be negative. Is it possible in any graph that exists to start at a vertex, wander around, come back, and have made $10? And the answer is yes. But if I do that, I've started at a single vertex, ended at the same single vertex. In other words, I've walked in a circle. Now, although the path doesn't have to be entirely a cycle, the path has to at least involve a cycle. And if I get back and I end up having made money, what I have is a negative cost cycle. So it is possible, theoretically at least, that the minimum cost of travel from a vertex to itself could be less than 0. The only time that's ever going to happen is if there's a negative cost cycle. And of course, in that case, that means the minimum cost actually goes to negative infinity. Fortunately for us, we are assuming, so look at the theorem, the graph has no negative weight edges. There is no way I have a negative cost cycle, and so therefore I do not have to worry about that case. The minimum cost of travel from a vertex to itself in a graph with no negative weight edges is actually going to be 0. Okay, that's good. But I did, just to be clear, I am aware of the case where you could somehow make a profit by traveling from a vertex to itself. That's an unbounded case. We don't have to worry about that here. Okay, so that's my basis. My induction hypothesis is, well, suppose the theorem holds for all vertices up to and including some vertex Vi. In other words, suppose that everything is good, that all vertices added to the tree up to and including the vertex added at iteration I of my outer loop have the property that when they are added, the cost in the cost array is the true minimum cost. Now my induction step is, consider the vertex V of I plus 1, that I add to the tree at iteration I plus 1. But right off the bat, because I chose Vi plus 1, like we know what the algorithm does, because I chose it, that implies that the cost of Vi plus 1 is the minimum cost value for a non-tree vertex at that step. Now it is possible that there are other vertices with the same cost, but there are no vertices with a lower cost. So we're going to sort of need that in a minute, so just so we know that. That falls right out of the algorithm, but I just wanted to make sure I put it in writing here. There are going to be 2 cases, and they're going to be sort of weird. That is, one case is obvious. It's unclear why the other case has to exist, but it has to do with a sort of chicken and egg problem, which is that it's obvious that the case doesn't have to exist once the proof is finished, or it's clear that the algorithm works correctly once you have a proof of correctness, but before you have a proof of correctness, you have to consider even cases that seem sort of bizarre. Okay, so here's what I'm going to do. We know that we're adding at this iteration this vertex here, Vi plus 1. Okay, Okay, we also know that if we're adding this at all, it means there has to be some path from vertex v start to vi plus 1. All I mean by that is that it's not an infeasible input. There's at least one candidate for the minimum cost path. Now, we don't necessarily know at this point, because it's what we're trying to prove, we don't necessarily know that the path that we're using, the path in the tree, so let's say, the path that takes me from v start to vi plus 1 through the tree, we don't know that that path is a minimum cost path. That's the thing we're trying to prove with this proof. So I'm not allowed to say, consider the path in the tree, which is a minimum cost path, because I don't know that that's a minimum cost path yet. So instead I'll say, because I know that there is at least one path, there must be a minimum cost path. Let's call that path P. And I'm not allowed to assume anything about the structure of P beyond what I can directly prove here. Okay, so there is a path from vertex v start to vertex vi plus 1. Therefore, there is a minimum cost path. Let's let P be that minimum cost path. Now, what's weird about this proof is that, it's a bit of an acquired taste. We can't guarantee that everything up to the last vertex of that path is in the tree. We want to say that. That is, what we're expecting to be the case is that a minimum cost path from vertex v start to vi plus 1 contains a bunch of vertices in the tree, and then it takes one step outside the tree to get there. That's what the algorithm actually does. We don't know that for sure yet. So for now, all we know is that P is a minimum cost path from vertex v start to vi plus 1, and it may or may not be partially contained inside of the tree. Certainly it starts inside of the tree because v start is obviously going to be in the tree. Okay, so P is a minimum cost path from vertex v start to vi plus 1. There could be more than one of them, but it's one of them. Now, let vertex u be the one vertex before vertex vi plus 1, so the second to last vertex along that path. Now, we from the subpath lemma from the previous lecture, we must have the property that this path here, the subpath up to and including vertex u, is also a minimum cost path itself. It's a minimum cost path from v start to vertex u, which means because we know that this edge is on the path from v start to vi plus 1, it's on path P, that the actual minimum cost of travel from v start to vi plus 1 is equal to the minimum cost of travel to u plus the weight of this one last edge. That just is implied directly by the subpath lemma. Okay, here are two cases. So case 1 is the one that we're expecting to happen. So suppose that u, that is the second to last thing along the minimum cost path, suppose that that's in the tree. Now, this is leaving open the possibility that v start and u are actually the same thing. So there's nothing about case 1 that prevents v start from being vertex u. There's no requirement that vertex u be separate from v start. There is a requirement that vertex u be a distinct vertex from vi plus 1. That's required, but vertex u could be the vertex v start. Okay, so case 1 is the case where u is a vertex in the tree. Okay, if u is in the tree, then I already added vertex u to the tree, obviously. And because it's already in the tree, I must have done so at some previous iteration. In other words, u is equal to vertex vj for some earlier iteration j. So remember that our hypothesis applies to every iteration up to iteration I, up to and including iteration I. So if u is already in the tree, then that means that it was added to the tree up to and including at iteration I. By the induction hypothesis, I know that every vertex added to the tree up to and including at iteration I had this property. And therefore, I know that this property applies to vertex u. Okay, great. And when I added vertex u to the tree, I would have relaxed this edge. Okay, so when I relaxed that edge, what would I have found? What path would I have discovered? Well, I know that I would have then computed the value of cost v, well actually, not quite yet. I do the relaxation, I compute cost of u plus the weight of that edge. We know from the previous slide that the cost of travel to u, which we know because of the induction hypothesis, the true minimum cost and the cost of travel to u in our array are the same number. We know that this sum is equal to the true minimum cost of travel to vi plus 1. So when I relax the edge from u to vi plus 1, I compute this sum, which I know from the previous slide to be equal to the true minimum cost to get to vi plus 1. And therefore, it's reasonable to assume that at the end of that relaxation, the entry in the cost array will equal this, because either the entry in the cost array was already this value, which means we're good, or it was a larger value, in which case we'll set it to be this, because this value is going to be smaller, because this value is the minimum. In any event, at the end of that iteration, at the end of the iteration where I added vertex u, u, the cost of vi plus 1 was the true minimum cost, and that means when I finally pulled in vi plus 1, of course this cost wouldn't have gone down, and so the theorem holds. At that moment, the cost was the true minimum. That's case 1. As I said earlier, case 1 is the natural case. That's how we expect the algorithm to work. The path that we discover is the one that goes up to something in the tree and then takes one step outside of the tree. But we haven't actually proven that, so we have to allow for a case 2, which is the situation where vertex u is not in the tree. Now this is weird, but at minimum, hopefully you can believe that maybe I'm being paranoid. You could argue I don't need to prove case 2 because case 1 should apply in all cases. Okay, you can argue that, but then wouldn't it just be playing it safe to prove case 2 anyway? Case 2 can't harm us. I claim that we need case 2. Even if you don't see the need for it, indulge me a little bit while I'm a bit paranoid with my proof to make sure I've covered all of my bases. Okay, so case 2 is, suppose that u is not a vertex in the tree. I have to do something sort of weird here to name a couple of other vertices. So here's what we know about the situation if vertex u is not in the tree. So we saw earlier, we have a path from v start that goes to some vertex. It follows some route to get all the way to a vertex u, and then u is directly before vertex vi plus 1. What I've shown is that vi plus 1 and u are both not in the tree. I know that vi plus 1 is not in the tree because it's the one being pulled into the tree at this iteration, so it wasn't already in the tree because that's how the algorithm works. Case 2 is saying u is not in the tree either. We know that v start is in the tree, because by this iteration, v start has to be in the tree. And so therefore, there has to be a first location where the path exits the tree. Now, there's a bit of nuance here, which is that we have no guarantee that the path isn't actually going in and out of the tree over and over again before it gets to vertex vi plus 1. That could be happening. So to be clear, there is no requirement that the path start in the tree, leave the tree, and then stay outside of the tree. My diagram sort of implies that, but that's not required. If we wanted to, we could design an example where the path might go leave the tree, go back in, leave, go back in again, and then finally settle at vi plus 1. So the path can enter and leave the tree over and over again if we're in case 2, for all I know. And actually, that could have happened in case 1, for all we know. All we said was that u itself was in the tree. We didn't guarantee that the path didn't leave the tree in the meantime, and it doesn't actually matter whether it does or not. This all seems bizarre, given that in our algorithm, the paths were always fully contained inside the tree. One way of approaching this in an open-minded fashion is to consider the fact that, yes, inside of your tree, there could be a minimum cost path that you've found that uses only tree vertices. But for all you know, there could be another minimum cost path of the same total cost that exits the tree and follows some alternate routing. We don't know how many different minimum cost paths exist. So as one way of treating this with an open mind, consider that that might be what's happening here. Okay, so the path begins at v start, and then it ends at vi plus 1, and it might enter and leave the tree a few times in the meantime. Let's consider the first time that it exits the tree. So we know that v start is in the tree, so the path begins in the tree. Let's consider the first vertex on the path that's outside the tree. We'll call that vertex y. And now, let's let vertex x be the vertex right before vertex y. So logically, vertex x has to be in the tree, and vertex y has to be outside of the tree. Now, it looks from the diagram, because the diagram is just an illustration for me to wave my hands at, it looks from the diagram as if vertex x and vertex y are somehow separate from all of the others, but that doesn't have to be the case. Nothing prevents v start from being vertex x, and nothing prevents u from being vertex y. Both of those could be the case. But in all cases, because y is out of the tree and x is in the tree, x and y must be two separate things. The reason why I had to do this complicated explanation of x and y is because I needed to define them in such a way that guarantees that both x and y exist and that they're not the same vertex, for what I want to do next. Okay, so by the subpath lemma, we know that this path here, the whole path P from v start to vi plus 1, we define that to be a minimum cost path. So the total cost of this path is this, the actual minimum cost. We know that the graph contains no negative weight edges, so the subpath lemma tells us that the minimum cost of a path to vertex u from vertex v start would have to be at most equal to the minimum cost of the path all the way to vertex vi plus 1, because we know that the part of path P that ends at U is a minimum cost path to vertex U. So we can actually generalize that to every other vertex on the way. The minimum cost to any vertex Q, so these are all various choices of Q, even this is a choice of Q, even this is a choice of Q. For all the vertices Q along path P, the minimum cost of travel to vertex Q must be less than or equal to the minimum cost of travel to vertex VI plus 1. Okay, that's one observation. That's just the subpath lemma doing some of our work for us. Okay, also, we know that X is in the tree. We also know that if it's in the tree, it must have been added to the tree already at some earlier iteration. And by the induction hypothesis, that tells us that the cost of travel to X in the cost array is the true minimum cost of travel to X. Okay, so keep that in mind. Now, at the time that I added X to the tree, well, we know what happens after I add something to the tree. I go and relax the edges attached to its neighbors. Okay, so I must have relaxed the edge XY. And that means that after that edge relaxation, so the edge relaxation itself would have computed the quantity cost of X plus the weight of the edge XY. And of course, we know from the induction hypothesis that cost of X is just equal to the minimum, the true minimum cost from V start up to X, as you can see down here. And I know that because this is the minimum cost of travel to Y, that by the end of this relaxation, the value of cost Y must equal this. Now, to be clear, I'm not guaranteeing that we didn't already know of some other path to Y with this cost. Like, there could be multiple ways of getting to Y, but I can guarantee that by the time I've relaxed this edge, the value of cost Y must be this thing. Maybe it was already, but it definitely is when I'm done. All right, additionally, because we know that Y is the vertex that comes after X along this minimum cost path from V start all the way to VI plus 1, then by the subpath lemma, we know that this segment of the path is a minimum cost path to Y. In other words, that this quantity here is the true minimum cost of travel to vertex Y. And so that means that one way or the other, even though Y is not currently in the tree, it is true that the cost in the cost array is the true minimum cost to vertex Y. Now, Y is a non-tree vertex, and that means that Y was one of the vertices we could have brought into the tree at this iteration, but we didn't. We brought in vertex VI plus 1. So way back at the beginning of this proof, we said, let VI plus 1 be the vertex that we choose to include at this iteration. And observe that that means that VI plus 1 must have minimum cost among all non-tree vertices at this moment. So Y is a non-tree vertex, and we didn't choose it, which means the cost to travel to vertex Y cannot be less than the cost of VI plus 1. It could be equal. There could have been a tie, but certainly if the cost of travel to Y were lower, then we would have brought in vertex Y instead, and that would have been a contradiction. If this were the contradiction version of the proof, we might have stopped there, or we might have found a way of getting out of the proof at this point. This would be our off-ramp. I'm not going to do that, though. I'm in the middle of a proof by induction. I can't go back now. Okay, so I'm basically just going to combine together all the relationships that we already saw. So one relationship was, because Y is in the middle of this longer path P, and we know that there are no negative weight edges, that means that the minimum cost of travel to Y is less than or equal to the minimum cost of travel all the way to VI plus 1. We also know that it doesn't make sense for us to have, as a result, it doesn't make sense for the cost, the minimum cost of travel to Y to be somehow greater than the cost all the way across. In the cost array, we can't have cost of VI plus 1 less than cost Y. And so we must have that the cost of VI plus 1 is equal to the cost of Y. In other words, as far as the question of why did we choose VI plus 1 instead of Y at this iteration, well, the answer was there was a tie. They both had the same cost, and we just chose to break the tie by choosing VI plus 1. Okay, so putting all this stuff together, we take this fact here, and we take this fact here. What we basically get is the property that the total of the true minimum cost of travel to VI plus 1 must be greater than or equal to the cost in the cost array for VI plus 1. But if we think about that, and maybe it helps if I write it in the from left to right, what I'm actually saying there is cost of VI plus 1 is less than or equal to the true minimum cost to get from V start to VI plus 1. And I hope you can see that clearly it wouldn't make sense for this to be less than. Here's the minimum cost. How could I have found a cost that's less? Clearly that doesn't make sense. So if I state this inequality, the only possible option is that the two things have to be equal. And that's what we're trying to prove. Because cost of vi plus 1 cannot be smaller than the true minimum, we can conclude that the two things are equal. And that was the theorem, that at each step, the vertex that I bring in the cost array, the value there is equal to the true minimum cost, and so we're done case 2. Okay, that was a lot of stuff. And therefore, by induction, when Dijkstra's algorithm adds that vertex to the tree, when it adds each vertex vi, the cost of vi is equal to the true minimum cost for every iteration I. And that proves that Dijkstra's algorithm does indeed find the minimum cost path tree as long as you have no negative weight edges anywhere in your graph. Okay, so we've proved the algorithm is correct. We only have one thing left to do, and it's not too difficult because all we're really doing is applying knowledge we already have about Jarnik's algorithm, and that is, can we speed the algorithm up by selecting the next vertex to bring in by more advanced logic that's a bit faster than linear search? And the answer is, well, yes, and it's the same thing we do in Jarnik's algorithm. We use a heap or some other data structure that's heap-like. And so I've rewritten the algorithm here to refer to that variation. I've changed the relaxation to be its own function to save space on the page, but notice that the function itself is not very exciting. It's pretty much the standard relaxation logic, except of course that I also have to do a key adjustment operation in my heap because I want to keep track of the cost of each vertex in a heap as opposed to just in a table so that it's easy to find the non-tree vertex with minimum cost at each step. And then line 10, where I actually find that vertex, becomes a remove min operation for a heap. So I begin by, I still create a table of cost values, even though we could argue that those are actually encapsulated in the heap or something. I still create that table, so maybe a bit of duplication in some cases. I also create a heap. I add my start vertex to the heap with total cost 0, which allows me to sort of condense my initialization into the general loop. And then I add every other vertex to the heap with infinity as its key, because at the moment, before I've initialized my cost table, I don't know how to travel from my starting vertex to anywhere. I'll figure that out when I, at the first iteration of my loop, remove the minimum element, which will have to be v start, because its key is 0 and every other vertex has key infinity, and then I relax its neighbors as usual. So the initialization sort of cleverly folds directly into the algorithm here. Okay, so in the heap-based version, I will, of course, in the worst case, I will perform this number of remove min operations. I'll end up adding every single vertex to the tree. Okay, so with an ordinary binary heap, that requires this amount of time. And then the only other real like bit of heap complexity, I guess, is the heap key adjustment thing. Although I guess the slides are pointing this out. When I want to construct the heap initially, I could actually do that in vlog v time, but I could also do something more. There's a bunch of optimizations I could apply here. I could use the heapify algorithm, and that would be linear time. But actually, because I know exactly what the heap looks like, I could just construct the heap explicitly. Just set the root to be v start, or the key for v start, and set every other thing to be the other vertices in any arbitrary order. I wouldn't need to actually use heap insertion to do this task. Okay, so because we know already that each edge gets relaxed exactly once in the worst case, so it gets relaxed at most once, that means the number of times I have to adjust a key of my heap is at most this number. And we saw when we talked about Jarnik's algorithm that heap adjustment can be arranged to be performed in this amount of time. And once we stare at the rest of the algorithm and observe that everything else is actually accounted for, we end up with this total running time. Total running time in this case is v log v plus e log v in the worst case, which is quite a bit better than the Bellman-Ford running time of number of vertices times number of edges. Although we should recognize that this algorithm, Dijkstra's algorithm, doesn't work if your graph contains negative weight edges, or you can't expect that it will work. You construct examples where it breaks. And therefore, if your graph contains negative weight edges, you might be stuck with the longer running time of the Bellman-Ford algorithm, or go out and look for some exotic solution that works around the negative weight edge problem. There are algorithms like this. I think one of them is called Johnson's algorithm that attempts to improve on the Bellman-Ford algorithm even in cases where edge weights can be negative. Now, with minimum weight spanning trees, it was very easy to turn this expression into something a lot easier. We could actually get rid of the v term here because we could observe that in a minimum weight spanning tree problem with a connected graph, that is to say a graph that has a spanning tree, the number of edges has to be at least equal to the number of vertices. We don't actually know that for the minimum cost path problem. That is, it is valid to compute minimum cost paths inside of a disconnected graph or a non-strongly connected graph, but just be aware that there could be infeasible cases. So that that means that really this is the most faithful expression for the general running time. On the other hand, if you know the graph is connected, so you know that the number of edges is at least equal to the number of vertices, or the number of vertices minus 1 or something, then it ends up being this running time, pretty much the same running time as Jarnik's algorithm. And as with Jarnik's algorithm, we can actually optimize it further by going beyond basic data structures. So if we use an exotic form of heap, like a Fibonacci heap, whatever that is, we actually can reduce the running time all the way down to this. And because you'll notice that this is less sensitive to the number of edges, this could be a pretty big improvement in graphs that have tons and tons of edges. I want to finish off with just a couple of examples of the heap-based implementation of Dijkstra's algorithm. So this functions on the left-hand side as just another practice input for Dijkstra's algorithm, but hopefully it also illustrates the way that the heap works. Okay, so using the heap-based version of Dijkstra's algorithm, compute a minimum cost path tree rooted at vertex A in this graph, and notice that the graph has no negative edge weights. If you are writing Dijkstra's algorithm and somebody hands you a graph with negative edge weights, it is their fault that graph doesn't, that you may get garbage output on that graph from Dijkstra's algorithm, because Dijkstra's algorithm cannot work with negative edge weights in general. Okay, so I begin by updating the table for the direct neighbors of v start. Now, in terms of the heap, what's actually happening here is I begin by adding v start to the heap with key 0. And as with Jarnik's algorithm, I have tagged the elements, the nodes of the heap, with the vertex that they refer to. The actual key in the heap will be the cost of that thing, but the tag will be the vertex that corresponds to it. Because when I remove the minimum element, I want to know which vertex I'm talking about. So the real initialization step is actually this one. I install my start vertex with cost 0 at the top of the heap, and everything else in whatever order I want with keys that are infinity. But in terms of what we've been doing for initialization, we view the initialization as being relaxing the neighbors of the starting vertex. This really happens at the first iteration of the outer loop in my heap-based version. So notice how I've already popped vertex A out of the heap at this point. I've removed it from the heap. So I do that. I then relax the edges to its neighbors. So I update B, F, and G. I, of course, make sure that those updates are synchronized with my heap, which requires rearranging my heap, obviously, so that the minimum element is still the root. But we know that that can be done in log n time. And then I just go through as before. So at this step, step 1, the non-tree vertex with lowest cost is B, so I add edge AB to the tree. And as part of step 1, I would be doing a remove min operation, so I delete B from the heap, and then I have to also update various keys in the heap as I update my table. So I relax the edges from B to its neighbors, all of these. I think only 2 of them get updated. It looks like there's no improvement of travel to vertex F, so I just update C and E. Those have to be updated in the heap as well. All right, now the non-tree vertex with lowest cost is C, so I add edge BC. And we can see our heap getting smaller and smaller here. Then the non-tree vertex with lowest cost is G, so I bring that in. And then the non-tree vertex with lowest cost is D. And then I add F. And then I add vertex E. Now, as before, the termination condition sounds a lot more, it's the same as before, but the termination condition here sounds more complicated than what I need. Notice that, first, the number of vertices in the tree is equal to the number of vertices in the graph, so I know I can bail out for that. Also, the heap is empty. And when the heap is empty, there are no vertices left to work with anyway, and so I can bail out based on that. What's neat about this is that I could then use the size of the heap in lieu of having to keep track of the number of vertices in the tree separately, because the heap contains every non-tree vertex. So when the heap is empty, there's nothing left for me to do. However, we haven't addressed the case where there were vertices left that were not reachable. But it turns out that our heap interpretation lets us do that really easily too. And it's in the pseudocode, but I think seeing an example would help too. So let's do the same exercise again on the same graph, except this time my starting vertex will be vertex B. I will observe, as with our earlier example, it's very clear that vertex A is going to be unreachable. There is no way for anybody to get back to vertex A. Okay, so my initial heap is this. Great. I begin by popping B off of the heap and then updating the table and the heap by relaxing edges to its neighbors. So I get this. The non-tree vertex with lowest cost is C, so I add that. Then I add vertex D. Then I add vertex E. Then I add vertex F. And then finally I add vertex G. And I'm done. So what's happening here is I can't continue. The tree will never contain all vertices, because if I go looking for non-tree vertices with non-infinite cost, I don't find any. The only non-tree vertex I could consider is vertex A, and vertex A has infinite cost. In terms of recognizing that case with the heap, Well, I could do a remove min and just verify that the cost is infinite, or I could just look at the root of the heap. And if the root of the heap contains an infinity, well, then I'm automatically done. Because clearly, there's going to be nothing below it in the heap that isn't also infinity, because nothing is greater than infinity, obviously. And so that's one other way of evaluating this termination condition. Okay, so we talked about ways of restricting the Bellman-Ford algorithm, for example, by by saying there are no negative weight edges, and also by analyzing the algorithm and seeing the ways in which it was doing duplicate, redundant work and reducing that duplication. We ended up discovering that we could adapt Jarnik's algorithm to produce something called Dijkstra's algorithm that computes a minimum cost path tree in a graph with no negative weight edges a great deal faster than Bellman-Ford in the worst case. And we then showed that we could optimize it just like Jarnik's algorithm. In the meantime, we did also prove its correctness and ended up with a pretty fast algorithm. One thing, though, that we've observed is that we've spent all this time computing the answer to the minimum cost path problem by finding a tree. That is, our original problem was to find a single path. I want the minimum cost path from vertex B to vertex E. And yet the way that we've solved that is by computing the minimum cost path from vertex B to everything. Now, there are ways of specializing it. So, for example, you could refine Dijkstra's algorithm to quit as soon as it finds the single minimum cost path you're looking for. But in general, in the worst case, the path you're looking for could be the last one it finds, so you might still need the whole tree. What I've done, therefore, is I've found these algorithms that with a single source are able to find the minimum cost path from that source to every possible destination. So I've been able to solve a whole batch of different problems at once. One question that I want to consider is, what if I try and solve an even larger batch of problems? I don't just want to find the minimum cost path from one source to all destinations. What if I want to find the minimum cost path from all sources to all destinations all at once? It seems to me as if I want to do that for all sources to all destinations all at once, I might be able to do it a bit faster by leveraging the fact, as we've seen already several times, that there are clearly overlapping subproblems present in the minimum cost path problem. And so really what I want to solve next is the all pairs minimum cost path problem from all sources to all destinations all in one go. And we're going to start talking about that problem at the beginning of the next lecture.